Thank you for that introduction. I'll be introducing the new functionality available in Simcenter Flotherm 2019.2. This is the most recent version of Flotherm. It was published to Support Center for download in December of 2019. The agenda for this part of the webinar is broken into two sections. The first part is called Improving Productivity and Workflow. Here I will introduce the re-engineered approach to post-processing in Simcenter Flotherm. The second part is called Enhancing the Thermal Digital Twin. In this section, I'll introduce the new functionality aimed at allowing you to better describe semiconductor package applications in Simcenter Flotherm. So let's begin by working through the Improving Productivity and Workflow section. So the first feature I'd like to introduce in this section is a new results mode. And this is by far the biggest change you'll notice when you install Simcenter Flotherm 2019.2. In previous versions of Flotherm, there was a module called the Visual Editor that contained all post-processing functionality. That has been removed in this release and replaced with this new results mode. One of the key things about this new results mode is that it is capable of creating plots and data orders of magnitude faster than in previous versions, which greatly reduces the amount of time you need to spend in the software to analyze your design. This is what it looks like. There is a toggle near the center of your screen that allows you to switch between model creation mode and results analyze mode. When you switch into analyze results mode, all of the post-processing functionality becomes available within the main graphics area of Flotherm. The functionality is partitioned as shown on screen. So we have the graphics area, which contains a visual representation of the model geometry plus any plots that have been created. Here in the screen capture, you can see a surface temperature plot of a printed circuit board and its components, and some velocity vectors in the background as well. At the bottom of the screen, you see a tables window. So by default, it will appear under the graphics area, but this is a dockable window. So you can position this anywhere you'd like. You can even drag it off to a second monitor if that's how you prefer to work. On the right side of the screen, we have a pretty standard setup. So we have a node tree to store the various plots that you may create. Each of the plots is definable and modifiable with a property sheet approach, which will always appear under the results tree. One of the best parts of this new results mode is the accelerated plot creation. So each plot type that's available has been optimized for performance and can now take advantage of multiple cores. So you can take advantage of any hardware that you have access to help you generate the plots faster. So all plots have been improved in this way. The biggest improvement that you'll notice will come with surface temperature plots. Surface temperature plots have been drastically improved. So there's a few things I can say about the performance that you can expect. So surface plots that used to be impossible, and what I mean by that are plots that were simply too complex for Flotherm to create. So they either failed or you ran out of memory and you couldn't generate the plot that you wanted. So those types of applications are now possible, and the plot will be available within a few minutes. Surface temperature plots that used to take a few minutes will now take a few seconds in the new results mode. So a tremendous speed up for most plots. The example that I have on screen is probably the best performance improvement that we've observed so far. What we're looking at is a Flotherm model, a detailed printed circuit board. So this was created using the FlowEDA bridge module to create a material map based on the routing on the top layer. So FlowEDA bridge created a model of this board that had over 22,000 objects. To create a surface temperature plot of the top layer in the old visual editor took over an hour, and in 2019.2 it took less than 1 second. So a tremendous speed up. And I have this model available, and I just want to jump into the software to show you how that works. So here we're looking down at the PCB geometry. I'm already in results mode, so I'm just going to go to the project node tree and select all of the objects in that top layer assembly. Click on this Create Surface Temperature Plot icon, and the plot appears almost instantly. In reality, it took just under 1 second for that plot to appear, which is many orders of magnitude faster than this plot was created in previous versions of Flother. So I'm very confident this will be an extremely popular improvement amongst our user base. That's not all we've achieved in terms of productivity and workflow. We've also revisited each of the plots that we support in an effort to streamline their creation. So I'll show you a few examples of what I mean. So in the instance of plane plots, and these are the plots where you take a slice of the model and you color it according to a certain scalar property. These can now be positioned by associating the plane plot with geometry. So the example that we have on screen, where we have a plane plot of speed, it has been associated with geometry, and it's linked to one of the fans that are sitting within that fan tray. So this helps you get the plane plot in the right location in the first instance pretty quickly. But even more importantly, if you decide to move that fan in a future model variant, then that plane plot will follow right along with it, saving you time for all subsequent models that you build. The other way we've made plane plots smarter is by allowing you to associate the plane plot location with a key result, and this is usually maximum temperature. So the setup for the property sheet looks like this. So the location of the plane plot is associated with the location of the maximum temperature in the model. So in this case, we can see that the plane of temperature in this case is coincident with one of the components that's sitting on the board. And that's useful because it's a pretty common thing to want to know, is where's the hottest location in the model. But if for this particular model, if I change the power distribution on the components, the next time I solve, the maximum temperature may be in a different location. If that's the case, the next time I enter results mode, this plane will automatically adjust its location to be coincident with the maximum temperature in the model, saving me a lot of time. In a similar manner, the particle plot definition has been enhanced as well to allow association with model geometry. So these particle plots are commonly used to help you visualize airflow within your product. So the particle plot can be associated with objects as well. So commonly it would be a fan smart part, or perhaps a perforated plate, or a resistance object used to model a vent. So this makes it easier to position the particles in the first place. And as I said earlier, if you decide to change the location of the fan in a future model variant, this particle plot will automatically follow right along. So I mentioned surface temperature plots a few moments ago in the context of accelerated plot creation. We've also made a change to how they're organized in the results tree. Specifically, they now have a node that you can access to fully define what geometry is present within the surface temperature plot. So this makes it much easier to retrieve a plot that you created earlier, turn it on or off, or make modifications as necessary. So that's it for now for the preview of the results plots in 2019.2. Now I want to kind of change topics a little bit and talk about the numerical data. So in previous versions of Flotherm, we had a tables application window that you could use to get access to the numbers behind the simulation results and use those to make your design decisions. So in previous versions, this tables window would operate by showing you everything about the model, and then you could find the information that you were interested in. And that works okay. It becomes more difficult when models grow in complexity. So Flotherm models have been growing. The typical model size now probably has somewhere around 10,000 objects. It could be larger. And presenting that much information at one time makes it a bit cumbersome to find the information that you're looking for. So in this release, we decided to turn the workflow around, and we've created something called on-demand tables. And the way this works is that you select objects in your model tree, and the tables window will automatically appear and reconfigure itself to show you only information that is valid for the objects you have selected. So in this case, I've selected 3 fans in my model, and the tables window will show me information about those 3 fans, and only information that's relevant to the fan smart part objects. So it works the same way for any object type. If I selected a monitor point in my tree, tables would show me only information about that particular monitor point. So it becomes very much a point and click operation to get access to the numbers that you need to have. To better support this type of workflow, Flotherm had to introduce new tables for all of the different object types. So in particular, their new tables are now available for source objects. So clicking a source object in the model tree will reconfigure tables to show you minimum, mean, and maximum temperature and power dissipation for those sources. If you select a perforated plate, it will show you the net volume flow and pressure drop and a few other quantities as well that are not shown on screen. If you select an assembly, this is interpreted by Flotherm as meaning show me all information about objects within that assembly. So if you select an assembly, it will report the minimum, maximum, mean temperature of all solid objects within that selection, as well as the total heat applied and some summary information about surface temperatures as well. If you select the heatsink, then tables will report the thermal resistance of the heatsink, the heat flowing through the base, min, max, mean temperature, and the solid mass of the heatsink as well. So each object type in Simcenter Flotherm 2019.2 will have its own table type that will appear if you select those types of objects. We've also made some changes to how transient tabular data is handled. So this was a very popular request from our users, would be to fully support tabular data for every saved time step. So that is now possible. So for transient applications, you will have access to a drop-down list that will show you all of the saved time steps. Making a selection here will update the table that is currently displayed to show you information about that saved time step. One can also export the entire transient variation of any of the tabular cells that appear with a right-click command to export table with transient data. And that will just create a CSV file showing you quantity versus time. Or you can simply copy it and paste it directly into a spreadsheet tool. Also, in the category of enhancements to tabular results, the find tool has been expanded to understand and allow interrogation of values that you could find in the tables window. So the find tool understands all of the results that could be present in tables. So some of the things you can do with the find tools now would be to find and select, say, all compact components that have a junction temperature greater than 75 degrees Celsius. Or you could use the find tool to find and select all objects that have a maximum surface temperature greater than 45 degrees Celsius. And there are many other examples of what you could do. So any type of tabular data can be built into a search query, which really streamlines the process to find interesting objects that have interesting results in your design. And the next feature in this category is offering full results within Command Center. So again, this is a pretty common request from our user base. So the new feature is in Command Center, for all scenarios that have full results stored, any post-processing feature will be available. So within Command Center, you can create particle animations, cut plots, surface temperatures. So this is extremely useful. I'll show you this in a few moments in the software itself, but it really helps you visualize results sensitivity to design parameters. So at this point, I'd like to jump into the software itself to show you a few features we've described already in the presentation. So here we are in Simcenter Flotherm 2019.2. I've selected a pretty simple model for illustration purposes. There is a fan object that's going to be directing air onto this printed circuit board. We have 8 components along the back, and we have a major power dissipator near the front, and a heatsink sitting on top of that. So to begin the tour, I want to show you some of the plot association aspects that I described earlier in the presentation. So the first thing I want to do is create a plane plot. I'll change the axis to be Z, and I would like to associate the location of the plane plot with the location of the maximum temperature. So I make that change, and the plane automatically changed positions. So apparently the maximum temperature in this model is within that component that has a heatsink on top of it. If I want to see what the value is of that maximum temperature, I have a little tool I can use to create a maximum temperature annotation. And there we go. The other type of plot I like to set up is a particle animation that emanates particles from the fan smart part. So to take advantage of that associativity, I'll select the fan object, click on the Create Particles tool, and I have achieved my goal. So this particle source has now been created. It has been associated with the fan smart part that is in my model, and from here I can animate the particles and take whatever actions I would like to modify the plots. To access the tables functionality, so I have that fan selected. I'll just make sure my tables window is visible. So I have that fan selected. It reconfigures itself to show me information about that fan. If I want information about the heatsink, I can select the heatsink. It will show me the thermal resistance and various other quantities. If I want information about this particular component, I can do that as well. From here, let's look at the support for results post-processing within the Command Center module. So I'll start Command Center. And we'll go to the Scenario Viewer tab right away. I'll explain the scenario that's been set up. So here's the model. And the idea here is to explore the sensitivity of the results to the location of the fan. So these scenarios have already been set up, and they're intended to move that fan smart part across the face of the enclosure. So we have 10 different steps moving the fan across that face. So just like back in Flotherm, there's a results mode available in Command Center as well. All of the plots that I had created back in Flotherm are mirrored automatically into the Command Center scenarios. So there is my plane of maximum temperature, there is my particle animation. The reverse is true as well. So if I choose to create plots in Command Center, they automatically are reflected back into the main Flotherm application as well. Okay, so now I will just move through my scenario list. Actually, first, let me just set up the particle animation so we can see that running at the same time. And I'll move through my scenario list. And as I change the location of the fan this way, particle animation will follow the fan. And I'd also like you to note that the location of the maximum temperature changes as well. So when the fan is directly cooling that heatsink, that reduces the temperature of that component, and the hotspot becomes one of the other components that's downstream on the board. Okay, so I think this is a great way to visualize design sensitivity to key parameters. I hope you agree and find this useful. Let's go back to the PowerPoint presentation and continue with the material. Okay, so next up in productivity and workflow is solid and fluid temperature. So again, this is another long-standing request from our users to split the temperature field into two parts. So we've achieved that for 2019.2. So 2 additional scalars are present for each model, solid temperature and fluid temperature, and they should be available for all plot types. The complete temperature field is still available as an option, of course. Okay, productivity and workflow. The next feature is dealing with scripting. So for a number of years now, we've been building up this new file format called FlowScript, and FlowScript essentially is a set of instructions that Flotherm can understand and play back. So it's very analogous to recording macros and other tools and then playing them back to help you automate some tasks that you may have. So it's the same idea in Flotherm. So with the extensions to post-processing in 2019.2, all of the post-processing features that you've seen today are now scriptable and can be fully automated. So FlowScript commands are available to create plane plots, to create particle animations, to create a table and export tables. Everything you've seen has a FlowScript equivalent. And what that means for you in terms of productivity is that you can easily produce scripts to automate your post-processing workflow. For example, you could use a FlowScript to generate all images, animations, and tables that might be required for a report. Or if you can, you can choose to standardize your company's approach to thermal design reporting by creating a FlowScript and sharing it with colleagues within your group or within your division. So So for larger Flotherm simulations, to create content for a design review or for a thermal report can easily take up to half a day. For complex projects that have many hundreds of design variants that are explored, the amount of time you can save on the post-processing side quickly adds up. So on a per project basis, you can easily save hundreds and sometimes even thousands of hours of engineering time. So some examples of what you could consider scripting. So a flow script could be created to evaluate touch temperature criteria. So a script could be used to drive the edit find tool to find all objects that have a surface temperature greater than 45 degrees Celsius and create a surface temperature plot of only those objects. You could also use a flow script to automate results extraction for a selected printed circuit board. So a script could be available to find all monitor points, regions, sources, and compact components within a certain assembly, and simply export CSV tables for use downstream. Another example would be to highlight all failing detailed components. So a script could be created to find all monitor points that have a temperature greater than 100 degrees Celsius, add annotations, and create a screen capture and write that to disk, for example. So to help you understand what would be possible here, I prepared an example that we can run through. This is a video of a flow script being played back to help automate some steps required to generate content for a report. So in this case, I'll pause the playback for the moment. We have a fairly detailed Flotherm model. The script that will execute will take as an input a selected assembly, so we'll only operate on this particular selection. And the first thing it will do would be to create a surface temperature plot of the entire printed circuit board and components, which is occurring now. Then it will change the view orientation to look down the X, Y, and Z axis, and I believe an isometric view as well. And each time it changes the view, it will export an image file to disk. So the same surface plot from different viewing angles, and all written to disk, ready for inclusion into a report. The final step is to find all monitor points and regions, create a table, and save out a CSV file of that content. So here's the image files, here's the isometric view. And looking down the three Cartesian axes, there are two CSV files that are present. We'll open the monitor points first. So all of this was automatically created on your behalf by using that flow script. So that particular script really did a lot of work. For us, and the playback time was, what was it, maybe 10 seconds or so. To do that manually within Flotherm, you're probably looking at least 10 or 15 minutes for that simple use case. So in terms of improving productivity, I see a lot of potential for scripting applications to make your workflow within Simcenter Flotherm go a lot more smoothly. Next up, in terms of productivity and workflow, is something called lightweight assemblies. So I referred to this a few moments ago, but typically Flotherm models are just becoming larger and larger, with many tens of thousands of objects becoming more common and becoming more typical Flotherm models. So this lightweight assembly feature is aimed at decluttering the project manager tree by allowing you to designate selected assemblies as lightweight. And making something lightweight doesn't change the model at all. The objects are still present. The results do not change. It has no impact on the results that you'll get. The only thing it does, it will hide all of the child objects in the model tree. So only in the model tree, they're still visible within the graphics area. So this gives you a much simpler model tree to work with. It's much easier to understand and navigate and manipulate. Okay, the last part under productivity and workflow is offering support for Chinese language version of Flotherm. So if you live in that part of the world, I'm sure you'll be happy to see this. All the main graphics, all the text within the main application windows are now translated into Chinese for our users in China. So to wrap things up on the productivity and workflow side, you can expect to save, I think, easily hundreds of hours of engineering time per project, especially for complex models that have many tens of model variants that need to be supported. So you save that time in several different ways. The first of which is the plot acceleration feature. So plots appear on screen orders of magnitude faster. Full results in Command Center reduces effort duplication for your applications that require many scenarios to be created. You can expect to have reduced seek time for numerical results, and that comes in two formats. So first would be the on-demand tables, so the point-and-click approach to getting the numbers that you need, and also that fine tool support for tables. The last demo that we saw was that flow script functionality to reduce post-processing and report content generation time down to a fraction of the time it used to take in previous versions of Flotherm. And last but not least, a simplified way of working, a simplified user experience by designating very complex assemblies as lightweight assemblies so that you can declutter your project manager tree. Okay, so that was it for improving productivity and workflow. Let's now move on to see what I mean by enhancing the thermal digital twin. So like I said during the introduction, the features in the thermal digital twin enhancement are aimed at better describing semiconductor package applications. So there's two main features I'd like to describe. The first of which is supporting thermal conductivity as a function of temperature. So in previous versions of Flotherm, you could establish a linear relationship with temperature and thermal conductivity. To improve the predictive accuracy for semiconductor materials, it's required to move to a nonlinear definition. So in 2019.2, the thermal conductivity of a solid material can be defined with a tabular representation of temperature and thermal conductivity. So this option is supported for isotropic, biaxial, and orthotropic modeling options. So all three can have nonlinear temperature dependency for thermal conductivity. With this new level of complexity for material definition, it was important to enable the visualization of thermal conductivity fields. So in 2019.2, there are 4 new scalar fields available when looking at results. So the thermal conductivity in the X, Y, and Z directions, as well as the fluid thermal conductivity, are all available as scalars and should work with any of the plot types that are available in the results mode. Next, the next feature in this topic is dynamic thermal management with the controller smart part. So the controller smart part itself is not new in 2019.2. It was first introduced in the middle of 2019 in the 19.1 release. So this controller object allows the users to define operating frequencies for a device. So it's a list of frequencies that each frequency has associated with it a minimum and maximum temperature, as well as a power versus time curve. One of the limitations in the original controller smart part is that it had offered support for a single temperature sensor. So in Simcenter Flotherm 2019.2, this controller smart part has been extended to use multiple temperature sensors. So now in this release, you can still control a single heat source, but now you can have multiple monitor points which serve as temperature sensors for this smart part. The behavior is very similar to the original smart part. The subtle difference is that all the temperatures from the defined monitor points are used, and a maximum value is used to decide when Flotherm should change frequencies. So if the maximum sense temperature is greater than the maximum temperature for that frequency, then the controller will step down one level of operating frequency, and the opposite is true for the minimum temperature. The real benefit to this is that DVFS based thermal management strategies can be more accurately described and built into your Simcenter Flotherm model of a semiconductor package. So to summarize this part of the presentation, semiconductor package applications will benefit from improved predictive accuracy, and you'll make better design decisions as a result. There's two aspects to this as we've seen. The first is more realistic material properties for semiconductor materials and full support for DFS-based dynamic thermal management design. So with that, I would like to pass this over to my colleague Paul Rose for his part of the webinar.
Thank you, Byron. I would now like to move on to the features introduced to Simcenter Flotherm XT 2019.3, released in December alongside Simcenter Flotherm. Two major enhancements have been made. Simcenter Flotherm Package Creator supports a supply chain of electronic components to improve the workflow when including devices in your model. Secondly, further improvements have been made to the modelling of PCBs to enhance the accuracy of the thermal digital twin. So, starting with Simcenter Flotherm Package Creator. This new module is designed to rapidly create detailed thermal models of a range of electronics packages. As shown here, these can be included in thermal simulation in Simcenter Flotherm XT and, coming soon, Simcenter Flow EFD. Probably the most important thing to derive from a simulation is the junction temperature, as this leads to development of reliability predictions. The more accurate the thermal model of a package, the better the prediction. However, using traditional methods to create the component models to high levels of detail are extremely time-consuming. Simcenter Flotherm Package Creator is designed to reduce these timescales from days to minutes. The process to create the thermal model of a package is wizard-based. Currently, there are 15 package families to choose from. Selecting one of these options, as an example let's use the QFN, will launch the wizard. Typically, within a package family, there are a number of different footprint outlines. The wizard utilizes standard geodetic footprint outlines, so, to start the creation of the individual package, the user simply selects the appropriate outline from the list. The user is then guided step by step through other settings, either selecting the default values based on the geodetic outline or making appropriate changes based on their specific design. At the end of the wizard, the user creates a thermal model. This process then populates the package model tree with an appropriate set of smart parts, which together make up the construction. These will vary depending upon the package family. Each smart part has its own property sheet. Individual dimensions, materials, etc. can be altered at this stage depending upon the user's requirements. A three-dimensional view of a package is displayed, which can be moved around the screen to view from different angles. Additionally, items can be hidden or made transparent to view the internal parts of a package. Once the user is happy with their setting, the complete package can be exported from Simcenter Flotherm Package Creator and subsequently imported to Simcenter Flotherm XT. For example, our QFN is constructed from 6 different smart parts to fully describe the construction from die to lead frame. Let's take a closer look at some of the individual smart parts and their options. Here we see the die smart part. In addition to the basic geometry and material settings, the user can specify additional features such as a metallization layer and distributed sources around the die. Some of the smart parts also include options to control the modelling level. For example, here we see that the bond wires can be modelled individually or combined as a compact model, or indeed ignored completely. And the list of smart parts goes on to cover any individual parts required for the range of package types available. Once we have our thermal models of our packages, how can we use them? The simplest way to add these packages into a simulation project would be to save them into a library. From here they can be dragged into any project or added to PCBs in EDA Bridge using the Replace Component feature. To increase the accuracy of such models, for example, particular dimensions may have been applied without precise measurement first, it is possible to use the automatic calibration feature to match the model to a measured structure function obtained from Trista. This feature makes alterations to selected inputs and runs simulations to automatically match the simulated and experimental structure functions. This ensures any simulation results will be as close to reality as possible. A combination of the previous two slides ensures that we can carry out accurate PCB and system level simulation using our Trista calibrated detailed package models. Let's now move on to a second major feature released with Simcenter Flotherm XT and describe our enhancements to the PCB modelling. First though, I would like to explore some background starting with some of the reasons we might carry out simulations. Probably the most common would be to investigate the heat spreading in the board and any impact on component placing. These may well go hand in hand, as often we get component heating from others on the board and shadowing effects to cooling air streams from one component to another. Less common but still important are dual heating effects and interface material. To be able to perform these tasks, we need a variety of different methods that are both flexible, accurate and efficient. Currently, we have a number of methods ranging from a simple approximation based on an estimated conductivity value through compact and detailed, where the effective conductivity is calculated based on the percentage copper present for the entire board or on a layer-by-layer basis respectively. At the top end, we have the ability to represent the copper beneath a component as actual traces. These levels all have their advantages and disadvantages. As we move up through the levels, the accuracy improves, but also the computational overhead increases. So what can we add? Currently, when we import an EDA file, we can see images showing the copper traces in every layer. We can now transfer and use these images to create a highly detailed network assembly to describe the thermal performance of the internal structure of a board. We've called this material mapping, and in support, we have introduced a new modelling level in the PCB Smart part. As mentioned, we can create a very high-resolution representation of the exact copper distribution in a board. While this is a lot more efficient than modelling the copper traces as solid bodies, the result of explicit thermal territories, there is still a solution overhead. Additionally, any package models need to be detailed such that any contact with the leads or solder balls must match the copper pads. While it is now easy to create such components with Simcenter Flotherm Package Creator, information may not be available, or indeed, time may not be available to solve the large models. Hence, an option to reduce the resolution has been included. Switching to averaging smears the effect of the copper across patches defined by the user. Reducing the resolution reduces the computational overhead, but can still capture the gross copper distribution. This also allows the use of simple or resistor-based representations of a component where the contact with the board is across the entire footprint. Let us consider that last statement in an example and how we can impact on the board modelling with simple or two resistor components using the board from the previous slides. The biggest impact on this board may be the patch of copper in the top right-hand corner and how best to represent this accurately. The first option, we will use the detailed model where each layer is modelled individually but the copper is averaged. Next, let's use a material map with averaging resolution 50. With the detailed modelling approach, the local patch of copper is smeared across the whole area of the board. What began as almost 100% coverage in the local area is reduced to less than 20%. This may be even more extreme on connections to other layers and combines to reduce the ability of a board to draw heat away from the components in this area, resulting in high temperatures. A material map approach allows the concentration of copper to be represented and further includes the accurate representation of the interconnection to other layers. The temperature is lower. However, we not only get better accuracy, but there is also a reduced time to get the results. Thank you for attending this web seminar. We'll now move on to any questions.